Okay, so welcome to another in the series of looking at the Tiny Tapeout infrastructure. So we've done 3 of these before, and you can check them out. I'll link them up here, and they'll also be in the description below. So we've mostly been focusing on the MUX, and the last time we spoke was Tiny Tapeout 4. Now, Tiny Tapeout 8 is open, so join today. We've also got a demo scene competition, so check that out. But we're going to talk about a couple of topics, probably the improvement in the timing, the power gating, the new analog support. There's been a lot of stuff that's been happening, hasn't there, Sylvain?
Yes. Honestly, since Tiny Tapeout 4, there has been like a ton of that has happened. Tiny Tapeout 4 was the very first one that was using the MUX, I think. Yes.
We did a test on 3.5.
3.5, yes.
Yeah, closed beta.
Yeah.
And we also moved to OpenFrame, right? So now we've got more space.
Yeah, so that's the first one using that was Tiny Tapeout 6, I think. And we had a prototype Tiny Tapeout 5 silicon on OpenFrame that we just got back as well. So yeah, tons of things that's been happening. Anything in particular you want to start with?
I guess let's just mention OpenFrame. So if you look at the background of the image that we've got here, this is a decap of Tiny Tapeout 4, I think. Yeah, because I didn't have the 5 chips when I visited Switzerland. And this whole area on the left is the Caravel RISC-V processor, which we never use. So what we did was we moved to OpenFrame, which is another kind of integrated pad frame supplied by eFabless. So when you're on eFabless Chip Ignite, you've either got Caravel with the RISC-V and the memories and so forth, which is this here, and your design just fits in this square on the right, which is 10 square millimeters. But we moved to OpenFrame because we're not using Caravel, and that gives us, I think, 15 square millimeters. So we can now fit, I think it's 500 or so designs in now.
Yeah, 512 exactly.
So this was Tiny Tapeout 5. We had a total of 380 tiles. And if we just change to 6, you can see the aspect ratio is different. And we had 512 tiles. So it got that extra space by going to OpenFrame. Was there anything else that was good to mention about OpenFrame?
I mean, one thing that we didn't know about at the time, but we discovered is that going through Caravel actually puts some logic between us and the I/O, which adds some delay. And so we've actually noticed while testing the OpenFrame chip that we get better I/O timings, roughly 2 nanoseconds better by going to OpenFrame, simply because we don't have sort of the pass-through of going through some logic that Caravel added and that we don't want. So we have direct access to the pads.
And when was the first time we did the analog test? Was on Tiny Tapeout 5, wasn't it? It was using analog pins.
Yes, Tiny Tapeout 5 as a first analog design done by Harald using only 2 dedicated pins. So it's just a tile that we set aside near the border, and we directly connected those wires to the analog I/O pads and configured those pads as analog pads. They're also auto-routed, which means that the wires that they use are very thin, meaning they're also very fragile. Like you can only get a few hundred microamps out of them before you burn them out. So yeah, you gotta be careful when you play with that test design.
Yeah, and if you want to find out more about that test design, then I'll link the video up where I tested the ring oscillator and the DAC that Harold made. Okay, so maybe let's talk about what we had to do to enable the analog mixed signal support then.
Okay, so the first thing to enable analog and in general custom designs was the actual power gating, because in Tiny Tapeout 4 and the one Tiny Tapeout 5 as well, for most designs, all the designs are powered all the time. And so that really means we can't accept people doing their own GDS. We basically only took Verilog and then we synthesized it using a known working tool chain and process that produced the GDS, so that we're sure that that GDS doesn't have anything that can kill the chip, like a short between power and ground, that kind of things. Obviously, for analog designs, people have to do their own GDS, so they just send us the file. And at that point, we had two choices. Either we add some kind of process to validate that that design is not going to pose a problem, but that's very complicated to do in the general case. Or the other option, the one that we took, is that by default, all designs are powered off. They have no power, which means that there's almost nothing they can do to ruin the chip. And then when we select that design, in addition to routing the IOs to it, we also enable power. And so next to each chip, we actually have a power gate. Let me actually share my screen. So if we look at, this is the Tiny Tapeout 7, I think. And if we look next to each design, let me zoom a little bit. We have this thing. Let me actually hide most of the layer. I'm just gonna show metal 5 and metal 4 and maybe poly, so that we see what the designs are. Okay, so like this square here, for instance, would be a user design, and that's a user design. And next to it, every time there's like this long elongated thingy, and that's the power gate. That's basically one giant transistor with, if you zoom in, you see it has like the tons of fingers. And that's what's basically gonna provide power to the design. If you look at the VIA, for instance, maybe this. Okay, so these are the power straps. They contain the various power rails. This one is going to be ground, and you see that ground directly connects to the vertical power stripe. Okay, like here you see the VIA better. You have the VIA that directly connect the power strap to the user design. But for power, it's going to be this rail here, and you see that if you follow the rail, there's actually no connection whatsoever directly to the user design. What it does is it connects to the power gate, and then from the power gate here, we have a power strap that's going to connect to the user design and provide power only when that design is selected. So that's kind of the safety that we took. And then we have various power gate. This one is the one that we taped out so far. For Tiny Tapeout 8, we actually have new ones that have been designed that are slightly improved, and mostly also this one only supported 1.8 volt. But for Tiny Tapeout 8, we're planning to support 3.3 volt as well, especially for analog designs, so that you can design some logic that uses 3.3 volt internally. And we needed a new power gate so that you have, well, you'll have two power gates, one for the 1.8 volt, and then if you use 3.3 volt, you'll get another power gate next to it that switches the 3.3 volt. And those have already been designed. You can actually see them already. Some improvement is that they have a lower LDS on. So if I show all the fingers, these are all the fingers again, so like a giant transistor. Those are much thicker because 3.3 volt transistors are 0.5 long. There's also a bit of circuitry at the top here, because to control the 3.3 volt transistor, we need some level shifting. So this is doing all the level shifting. It also has an active discharge, so that when the project is turned off, we actually discharge any capacitance that's left, so that the project shuts down, and we don't have any floating rails, things like that. And it also has built-in decoupling. So if you look, you see there is a cap M layer here, and you can see here. So we have some MIM capacitors built into the power gates that provide some capacitance to try to improve the quality of the power that we provide to the user project, because no matter how many fingers we put, it still acts as a resistor in the power delivery network. So we're trying to do as best as we can. That's something that actually has been improved a lot from TT4 now to TT7 and TT8, is that we have a much better power delivery network. Not only we have thicker straps, we have thicker ring, we also have more connection to the pads. Before we were only using like one pad to the outside and we were only using one rail. Now we're connecting all the VDD rails together and all the VAA rails together, so that we have more connection to the outside again to try to improve power.
Nice.
So yeah, so this was like the first step to allow analog design and custom design, was to improve the power gate, and then in general also improve the power distribution. The next thing is actually, you can do analog designs that don't actually talk analog to the outside. Like you could have an internal PLL to your design, stuff like that, but we still wanted to allow analog connection to the outside. Unfortunately, we're limited in pins. So in our TT05 test, we just had the 2 dedicated pins, but that's obviously not scalable. We don't have that.
Yeah, they were
many
both
pins.
used by Harold's design. Yeah.
Yeah, exactly. And there is nothing we could do. So we had to add basically switches, analog switches that either connect or disconnect the user module. We name them analog mux. That's kind of the name that we give them, but in reality, it's just a switch on off that either connects the user module to external pins configured as analog, or just disconnect them. And these are those things here. So these you can actually easily see where the analog designs are on the chip, right? Because they're not filled entirely with digital cells. So
yeah,
we have a group here and we have a group here. They're placed that way because we have 6 analog pins on this side and we have 6 analog pins on this side. So we put them near where they're going to connect to try to reduce as much as possible the amount of connection parasitics that we have. And then we have those traces that connect to the analog switch, and the analog switch will connect to the user module. And those are pass gate,
transmission gates.
Transmission gates. That's the name.
I like the way you can see how much bigger the P transistor is than the N transistor.
Yes, I've tried to match sort of their resistance, and that means that the P is like 3.3 times the WL ratio of the N, approximately. And again, so these are the actual pass transistors, and this is going to be some level shifting logics to control those transistors to be able to drive them, because we want our analog pins to support 3.3 volts. That means our analog switch needs to support 3.3 volts. The kind of parasitics that we get, we still need, none of the chips that, we had the test chip from Harold, but that wasn't using those switches, that wasn't using this connectivity. So we can only, it was useful to test some things, and I have been able to sort of use simulation of Harald's taped out design and try to match it with measurements I made to try to estimate some parasitics and match some things. So for instance, I've been able to more or less match the estimated resistance of the wires and of the transmission gates. There are some tiny transmission gates in Harald design that allows to create an analog loopback. And so I've been able to measure the resistance of that loopback at different bias level. Compare that with SPICE simulation, including parasitics extraction for the wires, for the things, and get a pretty good match between the two. So that gives us confidence that the simulation results that we got for this design is hopefully going to match reality. And that should give us some pretty good connection to the outside. Yeah. Fingers crossed.
Yeah. Yeah. So one thing also that I found quite interesting is that as a user, when you submit a design, you fill in which each of you, it's like up to 6 analog pins, and you fill in which each one is, but you don't actually know which physical pin they're going to get connected to until we commit the final
Yes.
design. Why is that?
So there's two reasons for that. First, we don't really the placement. If you're going to be in that group or that group, we don't know necessarily it in advance. It's going to depend of the random of the placer, because some blocks are larger than one tile, and so we need to fit them together so that they actually fit. And the other thing is that the placer will actually try to balance, because if most people used 2 pins and we connected those to the first 2 pins, those 2 first pins would have a much higher parasitic capacitance due to everything that's connected to it, on it than the rest of the pins. And so what the placer does is that it tries to decide, okay, like this line has been used 4 times, this other line has only been used 1 time, I'm going to use that other line to try to balance them. And so the final decision is only done basically at the end when the placer is done. And you can actually probably see here, if I look at metal, so I need to look at those via, I can remove this.
No, yeah, you can see which wire they're connected to.
Yeah. So you have the output, and you can see that they're connected, and they will be connected different. So like here we have 2 modules. Each of them only use 1 pin, but they're connected to different ones. And that's decided by the placer, trying to, see what's best, what's more balanced. It tries to balance both the load. It also tries to balance the length of the wire, because that's going to affect both the capacitance, the resistance, and potentially the delay that you're going to see. So yeah, it tries to match all of that to the best of its ability. It's not like super advanced or anything, but for a simple algorithm, it works.
Yes, it's a good thing to pay attention to.
Yeah.
Yeah.
I didn't notice there are some funky drawings in this.
Yeah. It's finally getting some GDS art into Tiny Tapeout.
Yeah, I'm pretty sure. Wait, shouldn't there be... There should be some here, but it might be on Metal 5. No, it can't be on Metal 5.
Metal 4, maybe?
I am showing Metal 4 already. Here.
Oh, yeah, there you go. Got the high voltage.
Okay.
And they got a zero voltage one as well.
And here there's a... Thank you, Madven.
Cool.
There you go.
Yes, okay. And so anything else you want to mention on the analog side?
I think that's it for now. I'm really looking forward to having the TT6 chips to be able to test a little more, and especially to see like bandwidth and current and stuff like that. Like all the specs and current estimation of what you can do are on the Tiny Tapeout page. But obviously that will have to be faced against reality once we actually get the chips.
Yeah. Yeah. Okay. Well, maybe let's switch over to that then. Face against reality. So you have made some measurements of things so far. Do you want to share what you've measured?
Yeah. So the kind of measurements I've did so far. When you categorize them in digital and analog, mostly. So digital has been always testing the mux delay through the loopback design. So one of the test design that we put in almost all chip is a loopback, where you send a signal on one pin, it comes out on another.
And we put that at the end of the furthest mux to get the worst performance.
I don't think so, because we did put that design at several places in one of the TT, and we saw that it didn't make any difference really.
Okay.
And that actually matches simulation, is that the position where you are has very little influence on the delay, because even if you're very close to the control, you still need to charge that the whole line, vertical line, and before it can change. And the frequency we're talking to, the propagation speed over 1 millimeter doesn't matter. Like it all happens at the same time, pretty much. And that's what the SPI simulation showed, and that's what the test on the, I think it was on TT3 and 3.5 where we had that. No, TT3.5 and TT4. We had like the loopback design at a bunch of different places, and when I tested, like you can see some difference, but it's not necessarily related. It's not correlated with the position on die. It's more like random variation.
Yeah,
which could also be due because process variation across the die, that kind of things. But anyway, yeah. So we test that loopback. The things I've tested is that I/O latency is under 20 nanoseconds. It more or less runs around 18 nanoseconds for TT5.
Do you have that text file you can share?
The setup I tested is I just feed a 25 megahertz clock to a UI0, and I measured the output on different output pins, because the loopback actually sends UI0 to 7 different pins on the output, so that you can see the skew between channel and how much that can vary. That's my probing setup. I put a channel 1 on the input pin, and then I had an active probe on channel 4 to measure the output pin, to make sure that I'm not loading it and put any kind of loading on it. So it's the active probe is like 3 picofarad loading. It's really low. I did properly DoD skew, so that if I put the channel 4 probe, the output probe on the input, I'm at 0 skew measured, to make sure that all my setup is zeroed, and then I just measure the delay. You're doing a lot of average and slicing. When I consider the signal to transition at exactly 1.8 volts, which is like half the 3.3, or more or less. And here are the results. So if we look at TT4, we had latency, you can see between 25 up to even 13. First, we had a lot of variation. Yeah. You can see you have 13 nanoseconds, 25 nanoseconds. And it's in that range. So the large variation, I think it's because on that vertical spine, like those long lines, we have a very slow slew rate. It takes several nanoseconds for the signal to rise from 0 to 1.8. And so that means that depending on small process variation on where the receiver inverter, like the thing that's going to receive the output of that line, it might transition, sometime at 0.8 volts, sometime at 0.9 volts. And those small variation of threshold voltage are going to result in a large change in time. And I think that's why we have that in TT4, the larger variations compared to TT5. Because an improvement that we did from TT4 to TT5 is we actually split the spine in two. In TT4, the spline is one contiguous wire going the entire height of the chip. In TT5, we split them in two. So we have the upper spine and the lower spine. That means they're half as capacitive as before, which obviously improves timing a lot. And you can see like the reduction in delay has been pretty drastic.
And you think that is mostly to do with the splits of the...
So it is due to the split for sure. It's also due because when I did TT5, I also looked at the... TT4 was the first one we did with the new infra. And at that time, we didn't have timing analysis set up at all. In TT5, we did. So I took a look at the report, saw where some delays were, and I tweaked the size of some buffer and stuff like that to try to improve it. So it's improvement due to the split, and also because I resized some buffer and changed some things around to try to optimize the delay, basically. And so these are the new data. If you look, I tested one, two,
Yes,
approximately two
great.
sample. Yeah, like around 16, 15.5, 16 nanoseconds. The full time are slightly faster. That's always the NMOS are just
NMOS are just
better. Yeah.
electrons. They're always going to beat out holes, aren't they?
Exactly, and so that goes faster. That's something I'm still trying to improve a bit, is to have them more symmetrical. Some idea with that is that currently we transmit the signal as a positive signal both in the horizontal spine and in the vertical spine. But if we transmit it in one polarity in one spine and then in the inverse polarity in the other spine, one will tend to compensate the other, basically.
Yeah.
So you can try to improve things that way. That's still something I need to look at for.
It was like your Tiny Tapeout 3 hack where we reversed the polarity of the clock in between each.
Exactly. You try to balance where you pay the P price, so that you paid half in one polarity and half in the other, to try to balance things. And you can also see that they're more consistent, and that's probably because of the improved slew time. They're still slower than I'd like, but they're much better than in TT4. I also tested a bunch of OpenFrame sample, and what you can notice is that they are slightly faster, like maybe 2 nanosecond around-ish faster, and that's because we don't have the logic from Caravel. We feed the signals directly to the I/O pad rather than feeding them to the Caravel wrapper, which then makes it go through a bunch of logic, including, for some reason, some delay buffers, which obviously is not ideal for us, and then sends it to the I/O pad. So that gives us 2 nanoseconds. Now, I do expect a small degradation when going from TT5 to TT6, because although here it was an open frame, this one still only had 380 tiles. When we switched TT6 to full open frame, we increased the number of tiles, which increased slightly the size of the vertical spine, which again will degrade timing a bit. Yes, exactly. So I'm expecting that the TT6 will actually probably be similar to TT5 or somewhere between the two.
But a great improvement. Really good to see that.
Yeah. That's definitely nice. I actually didn't. Yeah, TT5 was really. TT4, sorry, was really slowish, honestly.
Still a lot better than the scan chain, eh?
Yes, obviously, like latency wise,
3 orders of magnitude.
You needed to count them in like microsecond, not in nanosecond. Yeah, all those numbers are in nanosecond. I know it's not specified.
But... Good to say that. Did you also get any measurements on the analog side of things for TT5?
Yeah, so the test setup for this is basically trying to measure the small signal resistance of the analog loopback. So what that means is you're trying to see how much the voltage varies for a given small increment of current on the analog pin at different bias condition between 0 and 1.8 volt. So you can see it as the DC, the RDS on of the transmission gate, if you want, of the loopback. And it's non-linear, because it's not a real resistor, it's a pass, a transmission gate. That resistance is not actually constant depending on which voltage you're at. It actually depends on the bias voltage you're at, and that's what this try to measure. The test setup is I'm applying a bias voltage to one of the analog loopback pin using a programmable power supply. And then between the two pins of the analog loopback, I'm applying a very small current, around 10 microamps, using an SMU and measuring the voltage delta that is created across the two loopback pins with that 10 microamp current, basically.
So it's a way of measuring resistance by having the voltage and the current.
Yeah, it does basically what your ohm meter does. Like it sends the current and measure the voltage, except here it's much more controlled. and it sends a much smaller voltage. Because if I try to use my voltmeter, my ohm meter, the current it tries to pass is like several hundred of microamps to even several milliamps, and that would destroy the pin instantly by doing that. So here I'm using a much more controlled and much more precise way of measuring the resistance, basically. Yeah. And so this is the typical shape that you see for...
So let me just get this clear. On the x-axis, we've got the voltage bias, and on the y-axis, we've got the resistance.
Yes, I mean, here in actuality, it's not the resistance, it's the voltage that has been developed. But given that it's at 10 microamp current, if you divide that by 10 microamp, that will give you the resistance in ohms. Yeah, I didn't do the actual math to when doing that plot. But you can here it's around 120 ohm. 1.2K here, 1.2K.
Okay.
To give you and then it just goes linearly. But that transmission gate that was taped out on the analog test has nothing to. It's not the same as the one we use in production, I would say.
No.
It's much smaller, so the one we're actually using to connect analog project has much better characteristics. But the idea was to try to match this to the simulation. And the two different ones, it's not simulation versus reality, it's OpenFrame versus non-OpenFrame. And the lower one is the OpenFrame one, and that just shows that even for the analog pin, the Caravel actually introduces some additional resistance, which is purely wiring. There is like around 1 kilo, the equivalent of 1 kilo ohm of wiring between the moment you make the connection in Caravel to the actual pin. And by using OpenFrame, we get rid of that parasitic. And so we just get this curve. And it's when you compare it to simulation, I unfortunately don't have the result here, but this zone and this zone really match very well. The middle doesn't match so well. It's actually lower than expected. But from simulating with mismatches and at different temperatures and with process variation, this middle part is it's highly variable because it's highly dependent on the process variation. That's
where you've got the two transistors like working together.
Yes, exactly. When you're at one end and when you're like, I think when you're at this end, the PMOS is doing most of the job. When you're at this end, the NMOS is doing most of the job, but each of them progressively degrades as you get toward the middle, because when the bias condition, let's say for the NMOS, as the bias condition increase, that means that your VTH is actually, your VGS is actually getting lower and lower. And at some point, that VGS is going to collapse below VTH. And at that point, the NMOS is useless. It doesn't do anything.
Turning off at that point.
Exactly. And there is some zone where both are still active, but they're not saturated. They're like more in the linear region, and that's why they exhibit some resistance in the middle. I think that's I think for me at least this, and I also did a test of bandwidth, which I didn't save the result. I just did a quick test with injecting frequency basically in the loop back and seeing kind of the frequency response. Oh wait, actually that. Okay, so this is another test I did on the loop back, is measuring the frequency response. Basically just injecting a small signal. I think I was using 100 millivolt amplitude at different frequency, and then seeing the frequency response. Here the axis is in decibel. The small spikes here are just measurement errors. You can disregard them. It's when the scope was switching between ranges. But you can see the curve here, and you can see that the -3 dB points, which can be considered pretty much the bandwidth here, is around 16 megahertz, which is pretty good because that transmission gate is really small.
Again, that's with the tiny transmission gate that Harold put in his design, right?
Exactly. That's that small transmission gate, and it's also very thin wires connecting to it because they were auto-routed. So I'm expecting I mean, I have good hopes of having several hundred megahertz of bandwidth for the future tiny tapeouts. I mean, not future, even TT6, 7, and 8.
Yeah, great. Okay, and I think we've also got some simulations of the transmission gates in the T-Gate repo.
Yes,
So if
yes.
you want to check that out, I can put a link to the designs in the description below. It's one of the great things about it being an open source project is being able to share all that stuff. Yeah. So, any last remarks for you? What do you hope? What's next? What have you got next on for next time we talk?
Well, so what I've been working on for TT8 is 3.3 volt support. I'm hoping to improve the loopback timing again. One kind of thing I'm looking into is actually the reason it's really sucks on the vertical line is the high slew rate, and that's because the tri-state buffer are slow. Essentially, yeah. And that's because they have two transistors in parallel, in series. Sorry, you have one transistor that control if the output is enabled, and the other that the classical transistor of CMOS that tells you if you go high or low. And those two transistors in series, first, they're not very well balanced for NMOS PMOS, and yeah, that's not optimal. And so I'm trying to design basically a new tri-state buffer that would have better characteristics and that could potentially be used to improve both the absolute timings and also the symmetry between rising edge and falling edge, basically.
Cool. So little tweaks to improve performance.
Yes, yes.
Nice. Great. Okay. Well, thanks very much for sharing all the work you've been doing, and look forward to getting Tiny Tapeout 6 at the end of the month. I think end of August we're expecting those chips, so we can do the measurements on them soon. And yeah, just a reminder, Tiny Tapeout 8 is open now. There's a demo seed competition. The closing date is 6th of September, so get involved. And thanks for watching. You can do a thumbs up.